We're just going to continue with chapter 11. Finishing. So far we've just dealt with sigma bonds. This is something called a pi bond. And a pi bond happens when we have multiple bonds, like a double or a triple bond. And what's the difference between a sigma bond and a pi bond? So if we take a look at a p orbital, there are two ways we can overlap two p orbitals. One way is by sigma bonding. That is, we'll turn one p orbital on atom A like this. Let's say it's a px, and then another p orbital on atom B, and then we'll have overlap here. This overlap occurs within the internuclear axis, and so this would be a p sigma bond. So p orbital on atom A, a p orbital on atom B. The other way these can overlap is if I have atom A like this and atom B like this. Even though they look like there's a node or a gap here, there isn't. What happens is we have overlap with these lobes here and overlap with these lobes here. And so this is a p pi bond. And this is just one bond. Like for example here, this is one bond because there's two electrons going to be shared here. And the same thing here, two electrons will be shared. Even though we have overlap in two regions, it's still considered a single bond. So, which one do you think is stronger, a sigma bond or a pi bond? It looks as if a pi bond is stronger because we have overlap in two regions, but when we look at the electron density and what holds the bond together, electron clouds can be more concentrated here because we have overlapping probabilities. And so what's going to happen, the two nuclei are going to be attracted to this negative charge density between the two nuclei. The same thing's going to happen here, except the electron cloud is going to be above and below the internuclear axis. So have concentrated. There's going to be a planar node right here. And so the nuclei are going to be attracted directly at each other, and the nuclei are going to be repelled by each other, but they're going to be attracted to the electron cloud above here and below here. If we do something called vector algebra, that is just add up these arrows, we'll see that the net movement is going to be towards each other like this. So they will be attracted to each other. It turns out, though, that the sigma bond, because we have two electrons worth of density here, the sigma bond is indeed stronger. We have more concentrated electron density in the internuclear region than outside. So when do we see sigma bonds and pi bonds in structures? We'll see that if we look at something like bicarbonate. This would be the Lewis structure for bicarbonate. Now, Lewis structures we don't have to draw accurately. So, for example, a lot of people will tell me that the HOC angle is 180 degrees because that's what it looks like. But it isn't. The HOC angle is not 180. Do you know what the angle is? The HOC? Ideal angle would be what? HOC angle.
The ideal would be
109. The ideal would be 109. It's going to be distorted because of two lone pairs. It's like water. It's bent about 105 degrees. But when we see a double bond like this, a double bond consists of a sigma and a pi bond. A triple bond consists of a sigma and two pi bonds. So we're going to see pi bonding occur in this double bond here. So let me draw it out. So we draw out the Lewis structure, then we're going to figure out the hybridization on each atom. So we're going to have three oxygens. we're gonna label these oxygens, maybe oxygen 1, oxygen 2, and oxygen 3. And then the carbon, only one carbon. And so we'll call this one oxygen 1, maybe 2, and 3. Clockwise. So the first thing is, what's the hybridization on the carbon? Carbon should be well, how many groups of electrons does carbon have around it? 3, so it's sp2.
sp2.
Yeah. sp2. sp2 has three sp2 orbitals. Oxygen 1, what's the hybridization? Oxygen 1.
2, 3 should also be sp2.
That should be sp2 also. So oxygen 1 is going to be sp2. Oxygen 2 should
That
be,
should be sp3.
sp3. And oxygen 3,
Also sp3.
also sp3. And so we'll just draw the energy level diagram for carbon. Carbon's sp2, 1, 2, 3 sp2 orbital. How many electrons does carbon have? 4. So is it going to be 1, 2, 3, 4? Does that look right to you? 4 electrons. Now, the way we fill these orbitals is we always have to pay attention to the Lewis structure. Does carbon have this? You know, I have 2 half-filled orbitals which can bond. So I'm capable of forming 2 bonds and I have a lone pair. And carbon should have, if I form 2 bonds and have a lone pair, it should have less than an octet. You should just have 6 electrons because you have 3 orbitals, 6 electrons. Is that what I see over here? I see that carbon has less than an octet, it has a lone pair and 2. No, this is wrong. And so whatever I do, I have to fill these to match the Lewis structure. And so I'm missing something. What am I missing? I'm missing a orbital.
P.
Yeah, I'm missing a p orbital. So there's a p orbital. In fact, I only use 2 of them, so there's one unhybridized p orbital here. And so when I fill these, it's got to fill like this: 1, 2, 3, 4. Now I'm capable of forming 4 bonds, and I'll have an octet. Otherwise, it wouldn't. And so we're going to draw this out here. Now I'm going to draw this. Let's see. Twist this molecule a bit, because it turns out there are going to be 2 Lewis structures for this. These are resonance forms. I saw the other day. So I can have the double bond on oxygen 1, or I could have the double bond on oxygen 2. Here I'm going to put the double bond on oxygen 2. Single bond on oxygen 1. Negative charge. Excuse me. So this is what I have so far. Now I'm going to draw this. Let's draw the carbon. Carbon's sp2, so what I'll do is a side view. You have a choice of side view or top view. And so for the side view, how should I draw this? I know what I'll do. I'm going to make this sp2 here in the plane, this sp2 coming out, and this sp2 going in. Because I know that sp2 orbitals form a trigonal planar arrangement here. And that should be good. And then I'll fill it. So I have 1 electron in each. And then where should my 4th electron go? Into the p. Now where's the p orbital in relation to the side view? Yeah, it's going to be vertical. It's going to be along the z-axis here. We'll do a different color. Now, I don't want to label it like this. I only put one p label here. I don't put two p labels because then that might get confusing because you might think you have two of the p orbitals, but we only have one of the p orbitals. So I can't label it. The p orbital has two lobes and it can hold a max of one electron. And so that would be the p orbital there. And so I'm going to move the orientation. So I'm going to put oxygen, let's see. Which structure should I do? We'll just pick one. When we do valence bonds and we have resonance forms, we have some choices. We can do it on either the resonance forms or the hybrid. Actually, both of these will yield a hybrid structure, which is a 50-50 mix. And so when we do valence bond analysis, did I mention this yesterday? We're going to just choose one resonance form. The hybrid is complicated with valence bond theory. And so choose one resonance form. Well, let's go ahead and choose this resonance form here. And so I'm going to call that oxygen 1. So if I look at oxygen 1, what's the energy level diagram for oxygen 1 look like? Oxygen 1 is going to be what hybridization? It's going to be sp2, so it's going to look similar. 3 sp2s and 1 p. Now, the number of electrons on oxygen 1? 6. So let's fill it. 1, 2, 3, 4, 5, 6. Is that right?
No.
So if I look at oxygen 1, it should have 3 lone pairs and less than an octet. No. So when I fill these, I have to fill it according to, again, the Lewis diagram. That means I'm going to put the 6th one up here, but if I put the 6th one up there, is that how you fill orbitals? No, because that would be higher energy. This would be an excited state. But the reason why we get this excited state is to maximize bonding. In fact, there are 2 reasons why we hybridize. We hybridize to minimize repulsions, and we hybridize to maximize bonding. So, minimize repulsions and or maximize bonding. And or max bonding. Well, in this case, we're going to maximize bonding here. We can maximize bonding by promoting this electron. That gives us the capability of forming 2 bonds on the oxygen. And so oxygen 1 is sp2. I'm going to write oxygen 1 over here. And now sp2 orbital on oxygen versus sp2 orbital on carbon. Are they the same size? No, actually one's smaller. Which one's smaller? Oxygen or carbon?
Oxygen's.
Oxygen, yeah, is that higher Z effective. So oxygen's sp2 should be a little smaller. Now, when I do oxygen, this is oxygen's sp2. This is carbon's sp2. Can I have the spins? Yeah, the spins have to be opposite. So, I screwed this one up. This oxygen should be spin down, not spin up. If I make this oxygen spin down, then what I can have is I can have an oxygen sp2 come in here, spin down, and bond to this orbital here. Likewise, I can have a carbon sp2 come in here and bond to this orbital, spin up. And so this would be called an sp2 sigma bond. And that would just be considered one bond. Now the double bond part of oxygen 1 in this structure here is from something else. we have two more sp2 orbitals. Those two more are going to contain lone pairs. An sp2 here coming out, and an sp2 here going in, both these lone pairs. Now, oxygen is going to have a p orbital, and like carbon, the p orbital you can orient like this. Oxygen should be a little smaller. The p orbital, and if oxygen is going to bond to carbon's p orbital like this, you'll see, even though they look far apart, we're going to get orbital overlap. And to show the orbital overlap, we draw a line here, just to show that these can connect each other. Because there's no hard wall here, the distribution goes out further. And I'm not drawing these very accurately. But anyway, carbons spin up, so oxygen has to be spin down.
So what you're saying is they're a lot closer to each other than what you drew them at?
Yeah, because actually the p orbital looks like this.
So
It's a lot fatter, I guess you could say, a lot wider. I drew it too narrow, too skinny. We draw it skinny so we could see things a little easier. And you can see some of the distributions there. But essentially, we're going to have orbital overlap there. And so this is what the double bond looks like in terms of orbital overlap. In terms of the electron dot density, when we look at the carbon-oxygen bond, oxygen is more electronegative, so it's going to draw more of its electron density. So here's the sigma bond. The sigma bond is going to concentrate more electron density here. We've got the sp2 overlap here. And it's going to be a polar bond. And then the pi bond's the same. The pi bond's going to have pp, the lobe above, the axis, and pp, the lobe below. And so when we look at this, we're going to see that the oxygen and the carbon are going to be attracted directly. This is the sigma bonding, and this is the pi bonding part here, where it's attracted above and below the plane. And so this is what we'll call a triple bond. Call it a triple bond, or what do we call it? It's called a double bond. All right, now we have oxygen 2 and oxygen 3. I'm going to, just to keep things simpler, oxygen 2 had the hydrogen, or oxygen 3 had the hydrogen? Oops, I didn't want to erase this yet. I didn't want to erase this yet because this oxygen 1, this oxygen 1 bonds in two places. And so oxygen 1 has an sp2 sigma, and it has a pp pi. And so here we can see this oxygen bonds in two places, the sp2 bond and the p bond. Okay, don't write it like this. Don't write oxygen sp2 and an oxygen p. This makes it look like two different atoms are bonding in two different orbitals. We should write it one atom bonding in two places, two different orbitals. The same thing from carbon's perspective. This carbon has an sp2 sigma, and a pp pi bond. And so this is the double bond here, and this is the double bond here. Now, which oxygen had the hydrogen? So I erased it. Was it oxygen 2 or oxygen 3? Oxygen 3. And so we'll put oxygen 3 here. What's the hybridization on oxygen 3? Oxygen 3 is hybridized what? This is not ozone, but oxygen 3. sp3? Is that right? Okay, so we're going to have how many sp3 orbitals? 4. How many electrons does oxygen 3 have? 6. Let's fill these up. 1, 2, 3, 4, 5, 6. Does that match 2 lone pairs, 2 bonds? The first bond is going to be an sp3, sp3, no, sorry, sp3, sp2. sp3, sp2 sigma bond. And unfortunately, I am doing it again. I need to flip this the other way because that's going to bond to carbon. And so carbon sp2 is going to come in here and bond to the oxygen sp3. So here I have sp3, sp2, sigma. All right, when I draw tetrahedral, because this is tricky because this orbital is projecting out, but I'm just going to write this kind of in the plane because I write 2 in the plane, 1 coming out, and 1 going in. And so this is not exactly the correct perspective, but we'll just write the tetrahedral the same. If I have this one, I got this one here. And then we want the atoms to be all in line. So hydrogen's just got an s orbital here. And so this oxygen I'll leave spin up here, and then I'll make hydrogen spin down. And so hydrogen comes in here, give it spin down. There's a hydrogen s orbital. And then I have 2 lone pairs. The 2 lone pairs are going to be in sp3 orbitals here. This is sp3, sp3. All right, now there's an interesting thing to note, and that is this hydrogen I drew in the plane, but that hydrogen actually can move anywhere. If it's like a tripod on the end, you could rotate the tripod, the legs on the tripod. So the position of the hydrogen, let's say the hydrogen is black here, the position of the hydrogen can rotate like this. And the reason it can freely rotate like this is because a sigma bond has free rotation. If I rotate this, I still have the overlap. The overlap is destructive. However, a pi bond cannot rotate. Because in order to rotate a pi bond, you have to break the overlap here. It's going to cost you energy. So we have to break the pi bond to rotate it. And so this is fixed and rigid, whereas this is freely rotating. And so this is called a conformation. I just stop the hydrogen right here and I draw it. Okay? And it's easiest to draw as many bonds as possible within the plane that you can. All right, so the side view just means we're looking at the p orbitals from the side. The top view is if we're looking straight down on the p orbitals. So let's draw the top view of this. In the top view, we could see the trigonal planar arrangement of the orbitals a little more clearly. So if we have carbon here, we're going to have an sp2 coming out here, an sp2 here, and sp2 here. So we have a trigonal planar arrangement of sp2 orbitals. And then the p orbital is going to stick straight out of the bore here. It's going to be perpendicular. And so one lobe of the p orbital sticks out, and the other lobe sticks in. We got the 2 lobes of the orbital. Let's go ahead and put the electrons in here.
Are we not gonna do O2? I mean the second one.
Oh, yeah, I forgot to do that. All right, yeah, O2. What's O2? Hybridization. The second oxygen has a hybridization of sp3. How many electrons? 7. 1, 2, 3, 4, 5, 6, 7. So it should have 3 lone pairs and 1 bond. Is that correct? Yeah. That's it. I need to flip this. Yeah. Now I'm learning. Here. And what's going to bond to this So carbon's gonna come in
Carbon.
here. Carbon with an sp2 is gonna come in here and bond. Okay. And so here, I'm gonna draw the oxygen 2 over here. Now, this is getting tricky because, not much space. And so I'll draw 2 in the plane, a lone pair, 1 coming out.
Doesn't it bond on the other side?
Yeah, it's on in the back side, and so
Oh,
maybe
okay.
I should dash this. I could dash this if I wanted. Dash this.
Oh, I see.
Yeah.
So the oxygen's back here, bonding to this sp2. So this is sp3, sp2 sigma bond, and then I have 3 lone pairs. So let's see, I have 1 coming out, and then 1 going in, 1 coming out. So make this one coming out. And then I'll have 2 in the plane, 1, 2, plane. So it'll go these lone pairs here. And the sp3, sp2 sigma bond. Do you see it? It's sort of. It's kind of tricky to see, so it's always good just to draw it the same way each time. But essentially, what I'm doing is I'm doing this with a pen here. I'm putting these 2 lone pairs in the plane. That means 1 is sticking out, 1's going in. This. But it's not great, the drawing here. Well, maybe I should redraw it. In other words, this drawing is not very accurate. Because if the tripod is pointed backwards, if one leg of the tripod's here, then the other 3 legs would be on the opposite side, which isn't the case here. So it kind of drew it funny. But it's okay. Probably should just draw it the same.
Can you choose any side to connect that extra, the O2? Or does it have to be on that side?
It has to be on that side. I mean, you mean, can I switch O2 and O3?
No.
Yeah, I can switch O2 and O3. But there's only one space left. This is the only space left. I can't connect it anywhere else. Yeah, normally I draw it like this. I wouldn't worry about carbon's perspective. I just, draw the oxygen 2 in the plane. Right? We'll put the 2 in the plane like this. 1 coming out, one going in. And then the 3 lone pairs. That would be O2. Or 1.
Isn't the sp2 sigma bond? Oh, okay, never mind. It would be the pp bond would be the pi bond, correct?
Yeah, this is the pi bond.
Okay.
This is the pp pi bond. I forgot to finish losing this one. Let's get that. And so we have a pp pi bond. And so that's 1 bond, and then the second bond is the sigma bond. Over here is the sp3, sp2 sigma in the back here. We got sp3, sp2 sigma. I think it's something like that. So we'll go to oxygen 1 over here. This is going to be a top view. So here we have the sp2, sp2 sigma. And oxygen is going to have 2 lone pairs. Those will be in the plane here. Now, all we did was took that molecule and rotate it 90 degrees. And so we'll have the pp. Now, the pp, well, we got an electron here. The pp, I'm going to show the overlap by doing like this. The reason I do it with these curved lines is so that we can see the sigma bond. If I choose just a direct line across here, it might get mixed up. Probably wouldn't because I'm using a different color, but This is normally the way it's done. And so if I draw one above here, one above here, one below here, one below here, that's not 4 bonds, it's still just one bond. It's just showing the overlap of the lobes above and the overlap of the orbitals below the plane. And so again, I have my sp2 sigma, and a pp pi bond. That's the double bond part. And then if I go to oxygen 3, what I'm going to do is, since there's free rotation here, this is my sp3 here. What I'll do is I'm going to rotate the sp3 orbital here so it's back in the plane. And then I'm going to throw the hydrogen on there as the H, the s orbital on hydrogen here. And so here I am going to have my S sp3 sigma bond. S sp3 sigma bond, which is the same over here. You know, this is the S sp3 sigma bond. And so I just rotated it so it's now still back, in the plane, because it just makes it easier to draw. And then I have one orbital coming out, one orbital going in. These are going to have the lone pairs in here. 2 lone pairs, 2 bonds. And then oxygen 3 is here, oxygen 2 is here. Oxygen 2 is going to be sp3 as well. So I have one in the plane, another in the plane, and one coming out, and then one going in. So these are going to have lone pairs here. sp3. All right, so this is the top view. This is looking directly down on top of the p orbitals. So we can get an idea of the electron cloud by just dotting it in here and paying attention to electron negativities, whether it's going to be distorted or not. Bicarbonate. Let's look at a triple bond next. Probably the simplest molecule with a triple bond is acetylene. So if you look at the acetylene, what's the hybridization on carbon in acetylene? SP. The carbon's SP hybridized. How many SP orbitals are there? 2. 2. You know, when you have an S and a P, it's 2 orbitals. We're going to get 2 orbitals. How many electrons does carbon have? 4. So does it look like that? No. We know if we have sp, we use one of the p's, that means 2 p orbitals are left unhybridized. And so what happens is, in order to maximize bonding, we're going to split up the electrons and promote those 2 p orbitals. So let's do this here. Both carbons are the same, sp hybridized. So we have to learn how to draw that. What I'm going to draw is I'm going to just draw the tilted side view. And so we can draw the sp orbitals like this. This is an sp orbital and an sp orbital. Each orbital has 1 electron in it. The remaining 2 electrons are going to go into the p orbitals. And then we have the pz and the py. So we'll do pz in blue. The pz. PZ has one electron in it. Well, this one's a PZ. And the PY, where's the PY in relation to PZ? Yeah, it'll be perpendicular. But rather than drawing it like this, where we're looking at it straight, bird's eye, we're going to tilt it at an angle a little bit. And so this is what I mean by tilted. And so I'm going to have the PZ one lobe come out like this, and the other lobe go in. That. And then I have one electron in the PZ. Like that. Just tilt it kind of at an angle so we can see a little bit of the side of the PZ orbital. Now the other carbon is exactly the same, except I'm going to have to flip all the spins the other way. And so the other carbon's sp, so I'll flip this one this way. And so what I'm going to have is I'm going to have carbon 2 come in here. Have carbon 2 come in here. It's going to bond with an sp here. Spin down. Oops. And then I have, what else do I have? I have a hydrogen. Right. Hydrogen's here. It's a hydrogen s orbital. It's going to be spin down. And so that's going to go to the other sp. I'm going to have a hydrogen s come in here. We'll go spin down. Okay, I think that's good. Carbon 2 is the same here. I'm not going to draw out the diagram. Oops. So this will have to spin up here. Now carbon 2 is going to have a PZ as well. PZ. And this will have to be spin down. And so do you see a PP pi bond right there? And so I'm going to have a carbon 2 PZ come in and bond. Just do it in blue. But carbon 2 also has a PY. And the PY, I'll do a kind of the tilted view again. This will be the PY. And the PY is going to have one electron in here. So do you see here? I'll draw 4 lines connecting them just so you can get a view of the sigma bond there without blocking it. Even though I draw 4 lines connecting those two orbitals, it's just still one bond. It's PY. PY comes in here and bonds here. You see this carbon bonds with 3 orbitals, making a triple bond. We're going to have 1 sigma bond and 2 pi bonds. If we were to map the electron density, it would look something like this. If we were to map the electron density, we'd have a carbon here of the triple bond. We'd see the sp sigma bond would have an electron density here. And then the p, this would be the z, pz pi bond of electron density here and electron density here. So there's going to be attraction this way, directly, and then there's going to be attraction for the pi this way. And then we have the py, the py is going to have a cloud here, and a cloud in back. And so there's going to be attraction up and down as well. So up and down. And down. So this is just a lot of electron density around a triple bond. Triple bonds are going to be 6 electrons total. Triple bonds, since we have all this electron density, triple bonds are going to be the shortest. They're going to be shorter than double bonds and shorter than single bonds because two nuclei are being pulled in. They're also going to be the strongest. These ones are going to be the hardest to break. There's a lot of electron density there. The triple bond. We're going to talk next about conjugated systems. Conjugated systems have alternating double and single bonds. Sometimes these are termed aromatic. And what we see, when we have alternating double and single bonds, we see additional stability come about. One of the classic examples is benzene. Benzene C6H6. And it consists of a hexagonal ring of carbon atoms with alternating double and single bonds. And then we have the hydrogens here. This is an interesting structure because if you look at all the carbons are the same. Hybridization. And what's a hybridization? SP.
SP, combining of orbitals.
SP, which one? SP, yeah, SP2. These are all SP2. In fact, we can draw a resonance form for this. Draw a resonance form. It's like this. Let's remove the double bonds. Adjacent position. These are the two resonance forms of benzene. It gets tiring writing all these carbons and hydrogens. And so if you're doing organic chemistry, you're dealing with lots of carbon and hydrogen. And so organic chemists, they don't bother writing the carbon atoms. They just show the bonds. And so the left structure would be shown like this. There's a skeleton structure, in which the hydrogens aren't shown. It's not because they aren't there. It's because you can figure it out easily if you know how many bonds. And carbon forms 4 bonds, so you can figure out how many hydrogens have to go there. And then this is just showing the bonds here: carbon-carbon double bond, carbon-carbon single bond. So that's that. And so this saves a lot of time writing out the structures, so you don't have to write every single atom. So these are the two resonance forms. Let's go ahead and just draw the structure. You know, we're going to bypass the energy level diagram, which you can. We'll just go look at the structure. Because we know what it is, and we can see how many electrons it has. We're going to do a tilted side view. So let's see if we can draw that here. Can you kind of see it? I'm not going to draw the orbitals too much in perspective, but it looks something like this. all these are sp2 orbitals. It's kind of a tilted side view because we're going to get a profile of the pz orbitals a little bit. Pz orbitals are going to be like this. You see the pz orbitals here? All right, now what we're going to have is we're going to have alternating double and single bonds. So let's pick a resonance form. Which resonance form do you want to do? It doesn't matter. Let's do this one. If we do this one, then it's kind of like this. I have a double bond here. And then I have a double bond here. And I have a double bond here. Do you see that? But take a look at how all the p orbitals are oriented in this structure. And when you look at it, they're all lined up. If they're all lined up, it's like water. You know, I'm going to put 2 feet of water here, and then 1 foot of water, 2 feet of water, 1 foot of water. What's going to happen is if they're all lined up like this, you know, what we're going to see is that they all overlap. There's no wall here. The probability distribution goes out. And so we get this overlap here. And what that's going to do is it's going to distribute the electron density, the pi electron density throughout the whole molecule here. I'm not showing the sigma. The sigmas are localized here. All right, I'll emit the electrons out of there. And so what this kind of looks like is this kind of looks like the hybrid structure of those two resonance forms. The hybrid structure would look like.
So those 2 pi bonds?
3 pi bonds. 1, 2, 3.
What's any position
Yeah. What's going to happen is it's going to look like this, where the pi electrons are spread out over the entire ring. And so what we call this is delocalized. For example, these pi electrons are localized. These pi electrons are localized to these 2 carbons here. Okay, they don't belong to these. But what's happening is nothing's preventing these from overlapping all the way around. And so what we can do is we can delocalize those pi electrons all the way around the ring, which is shown here. Okay, this delocalization lends or gives additional stability to the structure. And so here we can delocalize the pi bonding electrons over the entire structure, making it unusually stable as far as the bond energies go. How about something like this? Are those pi bonds localized or can they be delocalized? Well, they're localized. I see a pi bond on the left end and I see a pi bond on the right end. And those are stuck there. But can I spread those pi electrons and delocalize them over the entire structure? Well, what's a hybridization here? sp2, 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 sp2. They're all sp2s. Well, they're all sp2s, then sigma is going to like flatten the plane. And the p orbitals are going to be here. So I have a pi bond here and a pi bond here. But what's preventing it from, is there a wall here?
No, there's.
These two p orbitals are adjacent to each other. And therefore, they're going to overlap in terms of density. And so, again, what I have here is I have a delocalized pi bonding network. It's just alternating single and double bond. It's just because, you know, to have that, we've got to have sp2 hybridization. When you have sp2 hybridization, it's going to align all the p orbitals in this way. How about here? This is kind of hard to see, but in the scheme of things, in organic chemistry, this is the way it would look. How about here? Are those going to be localized pi bonds or delocalized pi bonds? What do you think?
Localized. Because it's not alternating throughout the whole thing.
Localized, right. You're going to have a PP pi bond localized here and a PP pi bond localized here, right?
Yeah.
But can I, I'm just going to connect those two. Is that going to work?
No.
Unfortunately not. And so this is going to be localized because I got this sp3 carbon screwing things up, right? It screws things up. This delocalization is can be a significant factor in stabilizing a molecule. So let's take a look at another example here.
So a delocalized molecule is harder to break bonds than a localized.
It's harder to break bonds. So benzene, the predicted bond strength is between a single and a double. The predicted bond strength is a 1.5 bond in benzene because that's what the hybrid is. The actual bond strength is stronger, quite a bit stronger. And this is called resonance delocalization, or just delocalization of electrons. Delocalization stabilizes things. You know, when things are concentrated and localized, it becomes less stable. It's like water, you know. You concentrate all the water, like say in Lake Oroville, and it becomes less stable than spreading out all that water. If you take Lake Oroville and spread out all that water to the entire state of California, would they be worrying about some flash flood there, or would the towns be evacuating below the dam? No. If you delocalize all that water over the entire state of California, it's nothing. But when it's localized and concentrated in that reservoir, it's high energy, higher energy. And so this is the idea behind. The electrons are kind of the same thing. Electrons are this cloud, this fog, this water, spreads out. It wants to delocalize. All right, why don't you do this structure for me? This structure is a very unusual structure because what we predict isn't what's observed because, you know, this factor of delocalization, this factor of delocalization of electrons are powerful. And so work on this.